Okay, hi everyone. This is Ken 422, Chemical Reaction Engineering, week number 12. And today we'll be discussing chapters 10 and 11 from Levenspiel. Specifically, chapter 10 will summarize some of the conclusions, basically from the last few chapters on choosing the right reactor for different types of reaction, different configurations and operations, etc. And then chapter 11 will be talking about basics of non-ideal flow. I'm just trying to introduce some concepts or the non-ideality and how to think about it when you know when you get a job as a process engineer, or when you end up on a plant, or when you are working on any type of project, whether it's in the chemical industries and any other type of industries, or even in any of the other ancillary areas. You need to have a good understanding of the non-ideality of the scenarios you're going to face. Okay, so there's also homework number 9, which is assigned, and this is due next Tuesday. I guess next Wednesday is correct because it's due on the 18th. So just the solutions video will also be posted as well. Okay, so the schedule for the remainder of the semester. This week we'll talk about choosing the right reactor, basics of an ideal flow. Next week we'll talk about heterogeneous reactions, basically gas-liquid reactions, gas-solid, gas-liquid-solid, liquid-solid. When you have different phases reacting at the same time, how does this affect your ideal reaction equations, etc.? We'll talk about this next week. And then after that, that'll be week number 14. So 12, 13, 14 will still be a review week. It will be the last week of the semester, so we're going to review the concepts we covered, throughout the past couple of months, and trying to summarize, or basically trying to develop maybe an equation sheet, or just summarizing the different ideas and the different concepts we've been dealing with. And then your final exam will be whenever it's scheduled. Look up the final exam schedule. It will be that time. We'll hold it live the same way we held the last 2 exams, and it will be comprehensive. So it will cover basically all your homeworks. So make sure you're comfortable with all your homeworks. And some of the slides, something you might get some multiple choice questions. So, just study everything basically. Anyways, okay, let's start with chapter 10, choosing the right reactor. And in this chapter, basically, we have 6 main rules on how to choose the best reactor and how to decide on what reactor you want to use for your system. And we'll go through the 6 rules. And rule number 1 is for single reaction. So for single reaction, the rule you need to follow is to minimize the reactor volume, which translates to a cost, basically. You need to keep the concentration as high as possible for as long as possible if the reaction order is greater than 1. However, if the reaction order is less than 1, then the opposite is true, right? So if your reaction order is larger than 1, you want to use either a plug flow reactor or an ideal batch reactor. If your reaction order is less than 1, then you want to use a CSTR. And these choices will help minimize your reactor volume and minimize your costs by keeping the concentration as high as possible for as long as possible if n is greater than 1, or keeping your concentration as low as possible for as short as possible if n is less than 1. Okay, so just keep this in mind when dealing with single reactions. And if you go back, you try to verify what we discussed in the slides, case 1, how it relates to your performance equation, you'll find out that this holds true. Okay. Rule number 2 for reactions in series. So to minimize the concentration of an intermediate, you should not mix fluids that are at different states of conversion, really. And this is, we discussed this a couple of weeks ago, where basically if you want to maximize the concentration of an intermediate and you have reactions in series, you don't want to mix fluids that have different concentrations of the chemicals on which the reaction rate depends, right? So I don't want to mix streams which are at different states of conversion. You don't want to recycle a stream with a very high concentration of the reactant with a feed which has a low concentration of the reactant, or recycle with a low concentration of the intermediate with a feed that has no concentration of the intermediate. You want to minimize this mixing of the different streams. So basically a PFR or an IBR will give a higher concentration for an intermediate ore. So if I look here, the graph on the left-hand side shows the concentration versus time when I have a series reaction. In this case, it's A goes to R, goes to S, goes to T, whatever the reaction is. And I'm looking to maximize R, maybe maximize S. Just basically trying to maximize one of the intermediates in my series reaction. And if I use just a PFR with no recycle, PFR does not have mixing along the axial direction. So there's no mixing of elements at different states of conversion. You can see that in this case, I can get, I can, if I'm able to control the reaction to stop at this point, I can maximize my concentration of intermediates. This is opposed to the case on the right here, where if I have a PFR with recycle, if I have a PFR with recycle, I'm mixing streams at different states of conversion, or streams which have different concentrations of my intermediates, right? So for example, my feed might have no intermediate, whereas my recycled stream might have a high concentration of the intermediate. So I'm mixing these two streams, and this will result in a lower concentration of my intermediate in my system. Similarly for a CSTR, where CSTR is perfectly mixed, so all the elements are always mixing. So here, at CSTR, you're always forced to mix the elements or the species at different states of conversion, right? And in this case as well, you won't be able to reach a concentration of R or S as high as you can achieve when only using a PFR or an ideal batch reactor. Okay, so to reiterate this rule, in order to maximize the concentration of an intermediate when you have reactions in series, you don't want to mix fluids that have different concentrations of the chemicals on which the reaction rate depends. Okay, reaction series, no, try to avoid the CSTR, try to avoid recycling in a PFR, use one PFR, a couple of PFRs in series, or maybe a very long PFR, just avoid mixing streams at different concentrations of your intermediate. Okay, rule number 3, again, we're talking about parallel reactions, and for parallel reactions, there are a bunch of cases. We talked about this extensively in the slides for this scenario. However, if we want to summarize them, we can say to get the best product distribution, low concentration of A, so A is your feed, and here the scenario we're talking about is A goes to R and A goes to S. I have a parallel reaction, A reacts, give me 2 products, and you want to favor one of the products, or these 2 reactions are at different orders or at different and have different kinetics. So low concentration of A will favor the reaction with the lowest order, right? So if A goes to R is the first order reaction, A goes to S is the second order reaction. If I keep my concentration of A low, then I'm favoring the first order reaction. I'm going to get more R. Conversely, high CA is going to favor the reaction with the highest order. So again, if I have a parallel system of reactions, I have A goes to R, A goes to S, A goes to R is first order, A goes to S is second order. If I keep my concentration of A high, then I'm going to get more S because high CA is going to favor the reaction with the highest order. And you can always derive this. So if you write the ratio of the reaction rates, first order over second order is K1CA over K2CA squared. You can always see that, if I want to increase this ratio, I want to keep CA low. If I want to decrease this ratio, I want to keep CA high. And this is similar to what we talked about in your previous homework and on the test as well. However, these are just back of the hand rules. You can always derive them and verify them using equations if you always want to double check or something. And the third bullet point here, if the desired reaction is of intermediate order, then some intermediate CA will give the best product distribution. So let's say you have A goes to R, A goes to S, and then A goes to T, right? I have 3 parallel reactions. And the first one, A goes to R is, let's say it's 0 order. A goes to S is first order and A goes to T, second order. If you want to maximize the concentration of S, which is first order, you want to keep Ca at an intermediate level. You don't want Ca to be very high. You don't want, if Ca is very high, then you're gonna favor the highest order reaction, which is A goes to T. If Ca is very low, you're gonna favor the lowest order reaction, which is A goes to R. So you want to keep it somewhere in the middle. The exact value of where you keep Ca in the middle will really depend on your K values or your kinetics. So now you need to maybe write your equations and start doing some math and, you know, see if C is greater than this and this, then this will happen, and looking at your different cases. And then the fourth bullet point, if all reactions are of the same order, then the product distribution is unaffected by the reactant concentration, and we need to use a high concentration to minimize the reactor volume. So again, if I have system of parallel reactions, let's say A goes to R, A goes to S, both of them are first order, or both of them are second order, that means that the concentration of A has no effect on the product distribution. So, you know, if I write my ratios, R1 over R2 is equal to K1 Ca squared over K2 Ca squared. Ca squared is going to cancel from the top and the bottom. So I just have a constant, right? K1 over K2 is just a fixed number, or it's a function of temperature only, and it's not a function of concentration. So in this case, technically, you know, on the test, you say you can pick this, you can pick any of the flow patterns, and both of them will eventually achieve the same reactant concentration. However, from a practical perspective, you want to maximize the concentration of A to minimize your reactor volume, right? So just two different ideas here. If you're, you know, if you have two parallel reactions of the same order, then the system is independent of the concentration of A, or the concentration of the feed. So in this case, the practical thing to do, or the best thing to do, is to maximize your concentration of the feed. And this way you're gonna minimize your reactor volume. And by minimizing your reactor volume, you're gonna minimize your reactor cost and your overall process cost as well. Okay, for complex reactions, okay, sorry about that. So for complex reactions, these are the rules we have to follow. So when you have a complex reaction, so for example, you have a system which is parallel with respect to one species and series with respect to the other, as we've discussed in the previous weeks, you need to break the reaction scheme into component parts, right? Then if the reaction scheme is a series with respect to A, then A should be in plug flow with no recycle. And if the reaction are in parallel with respect to B, then B can be introduced as is convenient at any concentration, since it's not going to affect. So what we said is, if I have a system of reactions where it's parallel with respect to A, for example, sorry, it's in series with respect to A and parallel with respect to B. So in this scenario, we're talking about say I have a reaction A goes, or you know, B plus A goes to R, and then B plus R goes to S. And so if I look at this system of reactions, it's series with respect to A and parallel with respect to B, right? And this is a complex reaction. This is what we describe as a complex reaction in this course. And if this is reaction scheme, if it's in series with respect to A, then I want A to be in a plug flow system. And then I'm going to introduce B at different points throughout my reactor to try and maximize the concentration of my intermediate, or the concentration of the product which I want. So in this case, if I want to maximize the concentration of R, if this is my PFR, I'm going to introduce A from here, as we said, and then I'm going to introduce B this way, you know, just introduce B throughout my reactor. And this configuration is going to maximize my intermediate, or this is the configuration you should be aiming for. And again, no recycle, should not have a recycle. And basically because a recycle is going to decrease the concentration of the intermediate for a series reaction, right? Because I'm mixing streams at different states of conversion. So yeah, this is the scenario for a complex reaction. We always go back and have a look at these slides we talked about. But as a general rule of thumb, try to remember this when dealing with these systems. Okay, rule number 5 for continuous versus batch operation. And I think we've touched on this before, but any product distribution that can be obtained with a continuous steady state flow can also be achieved in batch or semi-batch operation. So any type of distribution, whether it's a series reaction, complex reaction, parallel reaction, which you can achieve in a flow system, can also achieve in a batch or semi-batch operation. The main difference will really lie in the overall volume of the reactor and therefore your overall cost. However, from a reaction engineering or from a chemistry point of view, or a reactor point of view or a reaction point of view, I guess, you can always achieve the same performance of this reaction in whether a flow system or a non-flow system. However, again, the main difference will be in your overall volume of the reactor, and this translates to cost of the system and your capital cost of the system, and then other factors like how complex your flow patterns are and other next level or higher design considerations. So if I look here for a flow reactor, PFR, or a system of CSTRs in series, this is equivalent to having a batch reactor. I just dump all of the reactants at the same time. On the other hand, if I have a CSTR, one CSTR, or a PFR with recycle, this is equivalent to having a batch reactor. I'm slowly adding in the species. Okay, so these two systems are equivalent, and these two systems are equivalent. I can achieve the same product distribution in both of these, and in these scenarios and in these scenarios. However, if you're doing a pharmaceutical process, for example, your volume is very low and you want to maintain a very high control of the reaction, then maybe you want to use a batch reactor where you control the system much better than having a PFR with recycle. If you're on an oil and gas plant where you're just trying to pump out chemicals, or refine some crude oil, and you want to desulfurize through a reaction system, or you want to coke a system or whatever, then a batch reactor doesn't make sense. Your volume is too high and you have a very high concentration, so you want to use a PFR to minimize your economics. So other considerations start coming into play now. Okay, rule number 6, which is the last rule, and this we talked about this a lot in the last homework, where basically a high temperature will always favor the reaction with a larger activation energy, and the low temperature will favor the reaction with a lower activation energy. Okay, this is due to the Arrhenius law, K equals K naught exponential minus E over RT, or if you want H equals H naught exponential minus E over RT, whatever it is, all your thermodynamic type of exponential parameters. Higher temperature will favor the reaction with the higher activation energy. A lower temperature will favor the reaction with the lower activation energy. If you're having a hard time seeing this mathematically, try to convince yourself, check your negative signs. But this is the trend you need to always keep in mind when trying to use temperature to your favor to control product distribution. Okay, so this is the end of chapter 10. Again, it's a very simple chapter, and even 11 it's a short chapter. What I want you guys to do, I want you to read examples 10.1 and 10.2 from chapter 10, and they have some interesting discussions, and they're simple examples, but it will refresh your memory on some of the topics we talked about. Okay, let's move on to chapter 11, and here we're talking about basics of non-ideal flow. And just to introduce this chapter, so far we talked about your ideal batch reactor, your CSTR, continuously stirred tank reactor is very nice and cute. We assume everything's perfectly mixed. Your PFR, we assume that there is no mixing among the elements and very idealized flow patterns, or a lot of ideal assumptions when dealing with the flow. And these types of assumptions their validity stops as you move throughout your design process. So at a very high level design, let's say you're designing a plant, and you can use these reactions to give you a good estimate or an initial estimate of the overall volume of the reactor, which you can use for sizing. And Aspen Plus will use these types of ideal um, assumptions for designing reactors as well. However, as you start moving on through your project stages, you need to take a closer look at what's actually happening in this reactor. My flow patterns, are they ideal? How dense is, if it's a liquid reaction? What's the density of this liquid? What's the viscosity of this liquid? Is this liquid too viscous that is going to affect my flow pattern? Do I have gas which is flowing at a very high flow rate that I'm getting large bubbles that's just making the reactor shake? Is the temperature too high that I'm getting steam and I'm getting water hammering and other things? So you start to think about the non-ideal scenarios going on in the reactor and how to deal with them. And typically, if you work on a plant, a lot of these have been, you know, or if you work at a company which deals with these problems, there's usually documentation, success stories on how to deal with these things, and you just follow, or you just try to understand the approaches used to do that. However, once you start moving on to a new project, or you get some experience and now you want to lead the design of something, you need to try to give yourselves a chance to understand all of these things, or if not understand them in extreme details, then know that they exist and know the right tools to use to address them. Okay, so here we'll touch on that. So for example, let's say we have so up to now we've learned how to design reactor with ideal flow patterns, right? Your ideal batch reactor, continuous stirred tank reactor, plug flow reactor, and the assumptions we made. If you go back, I think it was week 3 or 4, we made some assumptions when deriving all of these performance equations, and a lot of these assumptions are very ideal, right? To assume that all the elements are mixed equally, isothermal, all of these assumptions to facilitate the math at the initial design. We've also touched on a bunch of other reactor systems, like we have PFR with recycle. We said PFR with infinite recycle approaches the performance of a CSTR. Having a bunch of CSTRs in series is performance similar to a PFR. Having a bunch of CSTRs in parallel is similar to performance to a large CSTR. Having combinations of PFRs or CSTRs in parallel, which you can use to try to maximize your fractional yield. Combining PFRs or CSTRs together, which you can also use to try and control your residence time if you have a unique reaction. And how to choose different types of reactors to maximize yield of a desired product, which is what we talked about a few minutes ago. Choosing the right type of reactor, different ideas to control the concentration, maybe control the temperature to try and maximize the yield of your desired product based on the order of the reaction, the type of reaction, etc. And all of these are scenarios you're going to deal with. So let's have a look at, and let's start introducing this non-ideality concept, and let's have a look at some of these reactors here. So these are typically your lab scale or bench scale reactors you might deal with, where you're doing, you want to test the reaction performance, or you're not really measuring kinetics. So if you want to measure kinetics or intrinsic kinetics of a reaction are usually measured at a much smaller scale than what's shown on this slide, because when you're trying to measure intrinsic kinetics, you want to eliminate any type of mass transfer or heat transfer resistances. So if I'm measuring intrinsic kinetics of a reaction in a lab, I usually do it at the milliliter or even smaller level. Extremely small volumes are usually spinning at a very high speed to try and eliminate mass transfer effects, etc. Once you get your kinetics, you want to test your reactor performance, you take it to this next level, which is shown on the slide. And these are called bench scale reactors or even lab scale reactors. And they're on the order of 1 liter to 1 gallon, right? So one, or maybe sometimes 500 mils, 300 mils maybe, is also commonly used in some areas. And 300 mils is a lot, where it can give you some insight into some of the other non-idealities in a reactor, such as mass transfer resistances, heat transfer resistances, As you can see on this guy on the left here, we can introduce a splarger and see the effect, for example, of mixing speed on the reaction performance. Some of them, you see this guy has a cooling jacket. You can investigate or have a look at the effect of, coolant flow rate on the reaction performance, etc. And, you have high pressure bombs here as well, where you can run the reaction at high pressure and do all types of things. And if I look at these reactors, are they perfectly mixed? So if I run an experiment in one of these reactors, say 300 mils, and I compare it to my, so this is a batch reactor, let's say this is a CSTR. If I compare this performance to maybe this CSTR here to my CSTR performance equation, ideal CSTR performance equation, will they match? If they match, then this reactor is perfectly mixed and my assumptions are valid, and this is actually what happens. However, in reality, even at this small scale, you'll find out that there's deviations in performance. So if you measure your concentrations in this reactor here on the left, and you compare it to your CSTR performance equation, ideal CSTR performance equation, you're going to find a difference in the numbers, right? And this difference is not due to the reaction, it's due to the your transport non-ideality. So it could be that, your heating jacket, you have your heat transfer coefficient actually reduces the heating by a bit, and you need to have a better control of your flow rate. It could be that, the mixing speed, it mixes only the inside of the reactor, but you have a V vortex and the corners of the reactor have no mixing, right? You have dead zones in the reactor. All these types of scenarios can show up, and these deviate from the ideal behavior. And if they occur at this small scale, now let's start thinking about large scale reactors. They start propagating a lot more when you have much, much bigger systems. And here you start deviating a lot more from the ideal performance. So here, this is a fixed bed reactor, it's a shell technology. And as you can see, this is 7 meters in diameter, right? And it's 20 meters high. And it's, it has 29,000 tubes inside. Each tube is 1.25 inch. Right, so this is a monster of a reactor, right? 7 meter diameter, has 29,000 packed tubes inside this reactor, and our tube diameter is 2.5, which is about 1 inch maybe. And they run 14 of these in parallel to basically convert syngas, which is carbon monoxide and hydrogen, into higher hydrocarbons like diesel, wax, etc., which they sell to the market. Okay, how close is, if I compare the performance of this guy to my PFR performance equation, how close will it be? It will not be close, right? You're gonna get a lot of differences, right? And usually your ideal performance equation will give you a much higher performance than what's actually happening in this unit, because your ideal performance equation assumes everything is ideal, everything is nice, happening to your favor. However, in this type of system, it's 29,000 tubes. Let's say 10% of them are plugged, right, are clogged, or in 10% of them the catalyst is dead, or the water cooling system does not effectively cool the entire system. All types of things could happen which deviate from your ideal performance. A second case here, again, this is a slurry bubble column reactor. This is made by Sasol, which is a South African company. And again, this is used for Fischer-Tropsch synthesis, which is converting carbon monoxide and hydrogen to hydrocarbons. And slurry bubble column basically means I have 3 phases inside this guy right here. I have a gas, I have a liquid, and I have a solid. So usually I have a mixture of liquid and solid in the vessel, and I bubble gas through it, and then the reaction happens in my system, and then I take the liquid out, I filter out the products, and I recycle back my fluid inside the reactor. And we're going to talk about these when we talk about heterogeneous systems. But generally, if you look at this guy, okay, which equations can I use? Maybe a CSTR. Maybe I can say, okay, maybe I can use a CSTR to try and predict the performance of this guy. Okay, some people did it this way. And if you compare the performance, your results are not going to be close. So there's a 10 meter diameter vessel, 60 meter high, and they run 2 of them in parallel. They have 3, they keep one offline, online, but they always have 2 running in parallel to make 34,000 barrels per day of product. Okay, so there's a lot of non-ideality here, and you don't really need to account for every small non-ideal performance in this reactor. However, you need to get as close as you can without affecting your plant design, without affecting your plant economics. Okay, so real equipment will always deviate from ideal scenarios. And how can you account for this? And this has been discussed for the past 50 years. And this was actually the reason, chemical reaction engineering was formed. People who studied chemical engineering a long time ago, they didn't have this course. However, before 1970, this course didn't exist. But once you had some oil economics happened, and now you had to do a lot of refining of the oil, you had to do a lot of crude refining, you had to convert this oil to products, and now people start thinking about reactors and how can we design reactors, and this course was introduced into the chemical engineering curriculum. But anyway, so going back to here, so to account for these non-idealities, we need to account for three factors. Okay, these factors are somewhat related, however, most of the time you can really separate them distinctly, and you can separate their effect distinctly on the reactor performance. And these reactors are, first one is the residence time distribution, usually called RTD, if you look in the literature, um, commonly referred to as RTD. And it's the residence time distribution of material which is flowing through the vessel. So if I have two species A and B, they're flowing through my, let's say I have a PFR and I get two products R and S. How long will species A sit in my reactor? How long will species B stay in my reactor? How long will species R stay in the reactor? And how long will species S stay in the reactor? And at what point does R start increasing and S start increasing? And at what length of the reactor do I have the maximum R? Do I have the maximum S, maybe with a function of time, function of length, function of diameter, whatever it is. But trying to understand the residence time distribution is an important part. Second thing is the state of aggregation of the materials, right? And by aggregation, I mean its tendency to clump or for a group of molecules to move together. So for example, if you have a solid particle in a very viscous fluid, you're going to get some clumping, and this state of aggregation is going to affect your reactor performance. If you have a gas, there is no aggregation, right? The gas just zips through wherever it wants, and there is no aggregation. And these two extremes will affect how your system performs. And the earliness and lateness of mixing of materials in the vessel. And this point 3 is really important when I have multiple reactants entering a system. And at what point am I mixing these reactors? At what point am I introducing these reactors, putting them in contact with each other? And this really becomes important when you have multi-phase reactions. If I have a gas reacting with a liquid, how quickly can I get the molecule in the gas phase to, start come in contact with the molecule in the liquid phase, right? Will this be at 25% of my reactor, or can I do it at 5% of my reactor? Can I control this mass transfer from the gas phase to the liquid phase? That happens very quickly at an early point in my reactor. Does it take a long time? And I have to give it some space for the flow to develop and for the bubbles to dance, and then for the molecule to move, okay? And controlling the earliness or lateness of mixing is important, or to try and account for these non-idealities. And we're going to have a look at just some of these, just touch on them. Let's start by talking about the residence time distribution. And when talking about residence time distributions, we have deviations from ideal flow patterns, can be channeling, recycling, or stagnant regions in the vessel. And if you look at the figure on the left-hand side here, these are your typical non-ideal flow patterns, or these non-ideal flow patterns exist a lot in the process industries. First one is stagnant regions. So if I have, let's say this is a PFR or maybe a heat exchanger, the same idea is valid, where I have some baffling, or let's say I have some internals, and the liquid zips this way, goes around the internals, flows, or maybe the gas goes around the internals. And as you can see here, as it's flowing, I don't have a lot of flow in this corner. There's nothing in this corner, no flow here, no flow here, no flow here. These are called stagnant zones or dead zones. And basically I have a volume of my reactor which nothing is happening in. I'm not using it to develop the flow. I'm not using it to make the reaction happen. It's just there, and it's a non-ideality. It's just a non-ideality you need to account for, and this is actually very common. And the second thing you can see here is you see this a lot when you have impellers as well. So there's a mixer, and as you can see, if I'm introducing the feed from the top of my CSTR, the mixer is not going to allow the feed to react with what's happening at the bottom, right? It's just short-circuiting it to the output. So if I introduce the feed from the top, it's going to see a very turbulent area here, and it's just going to basically leave again from the top without enough contact with the fluid at the bottom. Okay, so how can I control this to make sure that this is perfectly mixed? Maybe I can use an impeller with two, or maybe I can use an impeller with two heads, you know, maybe I can use a side impeller. Maybe I can have the impeller at a lower height. Maybe I can introduce the feed from the side. Many different options to deal with this. For this guy here, maybe you want to, instead of having all of them horizontal baffles, maybe I can make this baffle longer, this baffle shorter. Maybe I can have a vertical baffle. Maybe I can add an L pointing downwards here so that it just mixes this way. There are many different ideas, and you can use your imagination to think of all types of things to try and address these issues. On the other hand, or moving on to other common non-idealities, is channeling. And you see channeling a lot, especially when you have gas and liquid. One thing you need to remember when dealing with gas, liquid, or gas solid system is gas is smart. Right? And this is something you need to accept when dealing with the system. Gas will always find the easiest way out, and you need to find a way to force the gas to distribute equally along your column. And let's say here I have a counter current packed bed. I introduce liquid from the top, so I'm spraying liquid from the top, and I have gas leaving or gas entering from the bottom. And channeling is when the gas basically sees a lot of resistance here, just ignores it and just zips out from the side. And this is the issue. One of the issues with dealing with gas is smart. It will always pick the easiest way out. Sorry. It will always pick the easiest way out, and it's your job to try and determine what's or try to control the distribution of gas along the radius of the column and along the height of the column. And this channeling issue is a big deal, especially with distillation columns, even with absorbers, with strippers, with packed beds. You see this a lot. And then the other thing here is, again, you have short circuiting. If I have a packed bed and I introduce gas, the gas will never reach the solids which are piled here, right? It will just react to the surface and then exit, or maybe it will create a flow path and all the gas will zip through it. So I'm not using any of my solid catalysts, etc. So how can you counteract this? There are ways. Maybe I can make this reactor start spinning, right? Spinning disk reactor. This exists. It can solve this problem. Here for a packed bed, maybe I can introduce baffles, have trays, that's why you have trays. You have packing with certain design, which forces the gas not to zip through it. All of these different solutions exist to try and address these problems. Okay, and all types of process equipment, whether you're dealing with a heat exchanger, with a packed column, or with a reactor, this is unfavorable. You want to avoid it because it will always lower the performance of the unit, right? So for a heat exchanger, if you design your heat exchanger with a certain area, as we said, the area of the heat exchanger is what really controls its performance. If I design a heat exchanger with a certain area and I find out that 20% of the area is not being used, heat exchanger is not going to perform properly, right? Similarly for reactors, similar idea applies. So we need to have, in order to avoid this problem, we need to have a general understanding of how long each molecule stays within the vessel. So if I'm able to account for or get a gauge for how long the gas stays in this vessel and compare it to my ideal case, so compare it to the number I want, I can start now thinking of ways to solve this problem. So here, if I find out that my gas only spends 5 seconds in my vessel, but I want it to spend 15 seconds, okay, I'm comparing the residence times, and I need to try and change the design somehow so that the gas stays 15 seconds. Similarly here, if I see that the liquid, only stays for a certain amount of time, which is half the amount of time you expect, then you want to try and change its design until your residence times match. Okay, so let's move on to a second idea, which is state of aggregation of the flowing system. And you need to remember that flowing material is in some particular state of aggregation depending on its nature, okay? So if I have solids flowing, let's say you have sand flowing, sand flows very smoothly. There's not a lot of aggregation. What if you have, let's say, chalk flowing? If you ever seen chalk flowing or cement flowing, all they start clumping up, and I have a lot of aggregation in my flow. And this is solids flow, it's slightly different field, but the same idea applies. If I have a very nice low density, low viscosity fluid flowing, you can see there is no aggregation. If I have a very viscous fluid, you can see that you have, bumps in the flow, you can have some clumping, and it's not a very smooth flow, and it affects your performance. Especially now we have vertical flow, we have gas liquid flow, you have a impeller, you get different aggregations. And the extremes of the state of aggregation are on the left here, where I have gases and not very viscous fluids. And this is called the microfluid. Basically, your fluid is, if you want to model this, you can look at the different molecules, and the behavior should scale up, or the equations should apply with a lower correction compared to the left-hand side, where you have a macrofluid, where you have non-coalescing droplets, solid particles, very viscous fluid. And here I have molecules start aggregating, and you have packets of fluid or packets of flow. And there are two ways to approach it. You can either try to break these packets, or you can just live with them and try to make sure that these packets are used as efficiently as possible. So state of aggregation is the second thing which accounts for an ideal flow. And this happens, so when it comes to reactor system, this happens a lot in gasifiers, and in if you have a fluidized bed reactor, and these are all specific cases of reactors out there commercially, and dealing with aggregation is a big deal. And this is not within the scope of this course. It's probably within the scope of a graduate particulate flow course. So if you, or even if in industry, there's a lot of these courses for engineers, continuous education. If you get a chance to take them in your career, or if you go to graduate school, do that. It's a very interesting field. Okay, the third thing is the earliness of mixing. And here what I'm talking about is the fluid elements of a single flowing stream can mix with each other either early or late in their flow through the vessel. And this has little effect if I only have a single fluid. However, if I have two reactants or two fluids, then at what stage do I mix them, or or my level of control over the mixing will have a big effect on the process. So for example, if I have early mixing here, I'm mixing, we call it young and old fluid, and then I have a flat velocity profile. So maybe I can mimic the performance of a CSTR followed by a PFR in one unit. Uniform mixing, it's the same along all the vessel. There is not a lot of differences in the mixing profiles in different regions. And late mixing, I have more mixing in the later regions of my reactor compared to the earlier area of the reactor. And if you think about this, this is more, if I compare this to an application in the industries, then this could be equivalent to, let's say I have a system, it's full of liquid, and I'm bubbling gas. I'm bubbling gas from the bottom through it. And as you can see here, I'm bubbling gas, and I'm getting some liquid product at the top here, or maybe gas product. As I'm bubbling gas, I have a lot of mixing at this early stage, and then I have less mixing at this later stage, right? So I have early mixing at the first part of the reactor, less mixing at the second part of the reactor. For late mixing, this could be equivalent to having a countercurrent. Let's say I have a reactive distillation system, right? You're spraying liquid from the top, and you're introducing gas from the bottom, right? So I have liquid coming from the top and gas coming in from the bottom. At this bottom stage, there's not a lot of mixing. However, as you get closer to the source of the liquid, you have a lot of mixing happening. And if you can control this region, so if in this system, for example, if I can maximize this region from, people say, or, it's usually that this effect or this very high mixing region is only about at 20%. That's after 20%, the effect of the exposure disappears. So if I know that the effect of mixing is very high in my first 20% and I need more mixing, how can I push this to the next 10% or maybe the next 20% of the reactor? How can I control these regions of mixing for the benefit of my performance? On the other hand, maybe how can I design this liquid distribution somehow to maximize this region so that I have a higher mixing region, or you maybe have a lower mixing region, whichever is better for you. So controlling the state of mixing is an important parameter as well when dealing with non-idealities of your flow. Okay, let's move on. So basically, when trying to account for non-idealities, I need to account for these three things or think about these three things. The role of the residence time distribution, the state of aggregation, and the earliness of mixing on how they affect the reactor behavior. In some situations, one of these factors can be ignored. So sometimes, let's say you have no issues with aggregation, then you don't need to think about it. However, in some cases, it might be the most important factors. If you have a system which is highly aggregating, so you have a gas-solid reaction where the solid is always clumping, has a very high agglomeration rate, then it becomes critical to take a closer look at this, and it might be the parameter that actually governs your design, since its effect is much larger than the other two parameters. Okay, and these are examples of micro and macro fluid behavior. We talked about this. So in this case, I have a gas-liquid reaction. It's called a bubble column reactor. I introduce gas, it bubbles through my reactor in a liquid phase, and then I get either a gaseous product or a liquid product. Here the gas is macrofluid because the gas bubbles tend to clump together and make larger gas bubbles. In this type of system, you want to keep your gas bubbles as small as possible because a smaller gas bubble has a much higher surface area to volume ratio compared to a larger gas bubble. And in order to maximize mass transfer, you want to keep your surface area as high as possible. So you want to keep your gas bubbles as small as possible. However, if your gas bubbles tend to, clump together to make larger bubbles, then this is an issue you need to deal with. How can I control my bubble size distribution? How can I control my gas residence time distribution? And in this scenario, gas is a macrofluid, the liquid is a microfluid. On the other hand, you have a spray tower reactor. The gas is a microfluid, liquid is a macrofluid, because I'm spraying liquid droplets on the top. And in this case, this is the opposite of this. Here, the gas is being dispersed in a continuous liquid phase. Here, the liquid is being dispersed in a continuous gas phase. So the same idea happens, however, from the opposite side, I want to control. So on the right-hand side here, I want to control my droplet volume, because a smaller droplet will have a higher surface area to volume ratio compared to a larger droplet, and a higher surface area to volume ratio means I have a higher area available for mass transfer. And so I'm able to control this somehow avoid these liquids from agglomerating and forming a macrofluid, keeping these droplets as small as possible. I can get a better performance of this unit. Okay, so these are just things to think about. However, you should also even though you have macro and micro behavior, the residence time will also play an important role. So let's say you have two competing factors now. If I make my gas bubbles too small, then my residence time will be too low or too high. Then I need to start comparing different effects, because a smaller bubble, the buoyancy forces will be different. The speed at which it moves up a liquid will be different than a larger bubble. Similarly, a larger droplet the velocity as it reaches from the top to the bottom will be much different than a smaller droplet, etc. So now maybe you have some competing factors, you need to think about them, etc. However, we need to keep all of these in mind when looking at these systems. So for the next few slides, I'll talk about residence time distribution specifically and how how you usually measure residence time distribution in a lab or when doing the early designs of your reactor, etc. Okay, so what happens if the real internal reactor flow pattern is not described well by one of these models? So you have some data from your reactor, you compare it to your ideal equation, you find out that it's not ideal, this was a typical case, and how can I quantify this non-ideality? And here we're talking within the scope of the residence time distribution. So let's think of a simple experiment where I have a CSTR here, and I'm adding a non-reacting tracer, okay? And a tracer is, a chemical which I can track its flow throughout the system, and it will give me an indication, or to give me a representation of how your typical fluid or how your feed spends time in my reactor, give you an idea of the residence time distribution of your system. And I don't know, I mean, this idea of using a tracer is used in many different applications. You get in medical field and nuclear field and all types of field, even in mining, it's used everywhere. And it's a good simple experiment to do. So if I introduce my tracer as an instantaneous impulse into the reactor inlet, right? So I just add a drop of tracer, the concentration goes spikes, and this is called the Dirac delta function. I don't know if you covered this in your differential equations course, but it's called the Dirac delta function. And I just have a spike of tracer in my feed, and then I monitor the tracer as it exits my process, right? So I'm having a look at how this tracer behaves, or how this tracer behaves, and then this representation is identical to the normal process fluid, right? So if I add an impulse of tracer at the inlet in a CSTR, this is what you're gonna see. With time, you're gonna get an increase in the tracer, which is then gonna decrease in this format, okay? And this is the behavior, or this is the typical residence time distribution of any fluid element in a CSTR. And this type of experiment is common to try and give you an idea of how these systems behave. And one thing you need to, and then once you have this plot, the specifics of this plot make a big difference, like the length from here to here, the height of the signal compared to the height of the signal, the area under these curves, they make a big difference on how on determining how the system is performing, right? Okay, let's look at the same experiment, however, when done in a PFR. And these types of responses are called residence time distributions. In each case, the mean of the residence time distribution is equal to tau. Okay, so the average, let's go back here. The average of the signal here, let's say the average will be somewhere here, right? This will be my space-time of the CSTR. For a PFR, and this is what you see in a PFR, if I add a tracer as an impulse, it's going to come as an impulse after a time tau, after a time delay. If you took controls, you remember time delay, this is what you see in a PFR. Very similar idea. If I add an impulse of a tracer here, after a certain time, proportional to the length of the reactor, this is going to show up at the output as an impulse as well, also called tau. Okay, the form of the residence time distribution determines the conversion achieved in the reactor, exactly for a first order reaction with certain bounds for other reaction orders. So basically the area under this curve, we can determine the conversion from this system. And basically if we do an experiment and measure the RTD of a reactor, we can estimate the reactor performance. And this is good, especially when you have let's say have a large scale reactor and you just want to test the performance. You can always put it in some tracer and measure it as it comes out. And you can get a good idea of the reactor performance, you can get a good idea of this residence time distribution. If I put in a tracer and it comes out, my function comes out like this, something's off. My function comes out like this, something's off, reactor is not performing correctly. If I get a weird shape, maybe it just looks like this, things off in my reactor. I have to take a closer look at what's going on and what's creating this for a PFR. If this time is much longer than what you expect, you have a problem. If in a PFR you see this type of curve, you have a problem going on with your PFR and we need to take a closer look. And you can use these to actually estimate the reactor performance, compare it to your ideal expected behavior, and try to quantify some of the non-idealities in your flow as well. And tracers have been used to investigate all types of systems. And again, a tracer, I just put in an impulse, and I just measure how it. Again, this is time, right? I measure its concentration with time at the outlet of the reactor, and the mean of this curve from 0 to 0, the mean, the average. This is my space-time of my reactor. Okay. And again, we said this used everywhere, used in human bodies, with isotopes, iodines, all types of junk. Rivers and waters, they use it a lot. And oil reservoirs also used a lot. If you end up studying petroleum engineering, studying drilling, studying reservoirs, they use tracers a lot. And then chemical process equipment to diagnose mixing equipment, which is very similar to what we are talking about. Okay. Let's have a look. How do we find the mean? And again, this curve right here is called an E-curve, just for your reference. It's called an E-curve or an E-plot. Basically means E stands for experimental. Okay. So if I have a look at this curve right here, just let's see, pointer options. If I look at this guy right here, this is the curve I got from my experiments, and I'm gonna just discretize it into squares, as you did in Simpson's rule or whatever, trying to understand the area under the curve. And the fraction of the fluid that's leaving the reactor at the time between T and delta T is equivalent to the area under the curve between these two, or in this time period, right? So if I want to find how much fluid is leaving my reactor between 3 seconds and 3.1 seconds, you can just get the area under this curve, and this will be the concentration or the fraction of the fluid that's leaving the reactor. In order to determine the concentration, so for the final concentration of A, summation of CA batch multiplied by the EAT delta T, right? So it's a summation of the concentration in your reactor multiplied by the area of the curve as you integrate or as you add them up from the initial to the final time. Whereas, this is equivalent to this, so you can always integrate and get the area under the curve. So if I know the fraction of the fluid leaving a reactor between time T and delta T, so let's say I want to find how much fluid leaves my reactor during the last third, of my tracer time right here. So last third, let's say it's from this point to this point. I just get the area under the curve here, and this will be the fraction of the fluid that's leaving. And then if I multiply this fraction by my initial concentration, I can get my final concentration of the fluid leaving from this part, right? And then this you can use these types of charts to do this type of thing. And this idea is that if I divide it into different pieces mathematically, it's very similar to using this idea of having a segregated flow model, where basically I'm just assuming each element is like a smaller volume of my reactor or a bunch of PFRs in parallel. Okay, let's move on to introduce an idea here, which is important as well, which is the idea of dispersion in PFRs. And dispersion model is a word, if you end up working with plug flow reactors or packed bed reactors, the word you're going to hear a lot. And the idea of a dispersion model is, when dealing with ideal PFRs, we always assume that we have a flat velocity profile. Everything is nice. There's no mixing between the elements along the axial direction. However, in reality, I have a profile which is jagged, which looks like this. And these fluctuations are due to molecular turbulent diffusion, different flow velocities, etc. And how can I account for this? This is called dispersion, right? Dispersion basically means that some of the fluid in this zone is trying to move on to the fluid region in the next zone. You're going to see a similar pattern maybe here as well. And I have dispersion. So basically all these small packets are spilling into each other slightly. And you need to account for this dispersion somehow. And this is usually accounted for using a dispersion model. And the dispersion model, it's good to know that it exists and good to know just the general how it looks. However, It's not within the scope of this course. It might be within the scope of a graduate level reaction engineering course. However, um, it's a system of equations used to represent this non-ideality. And in order to do this, I'm gonna take it's a second order partial differential equation where partial c by partial phi, or this is actually time, right? Phi is t over time, this dimensionless time. And this is equal to d over ul, this is your dispersion number, partial squared c by partial squared z. Again, it's a different, or partial differential over length minus partial c partial z. And again, if you want to model it in 3D, you're gonna have partial c partial z, partial cx, partial c partial x, partial c partial y as well. And you get a huge differential equation which cannot be solved analytically, has to be solved numerically. And there's a whole bunch of literature out there, a whole bunch of books discussing this. What you need to know is dispersion model accounts for the spillage of a fluid from different elements due to turbulent diffusion, due to molecular diffusion. And the way to model it is usually using a second order differential equation, which is a function of unsteady state against a function of time, second order differential equation, partial squared by partial z squared, okay? And a lot of the times as an engineer, you're not going to reinvent the wheel every time you see a plug flow reactor and solve 60 partial differential equations, right? Doesn't make sense. So what you do is you look at charts, and this is what engineers like to do. You have a bunch of charts for everything, performance charts, historical charts, historical performance equation charts, all types of things. And you can look at these dispersion, you can look at these charts to try and gauge the dispersion model of your PFR, or, and a lot of these charts are obtained from tracer experiments. So here, if, solving this equation might cause a lot of errors. So if I just put in a tracer and measure the concentration of tracer at every point in this reactor, at the beginning of the reactor, at the end of the reactor, I can get a good understanding of the amount of dispersion that's happening without actually solving this complex equation. Of course, if there are very fancy tools out there which can solve this equation for you, however, typically this has been the conventional way to do it, where you look at charts, tracer response curves for closed vessels, and large deviations from plug flow. And you can see, you can look at these curves at your own time, just try to examine them closely and try to get an appreciation for the type of thing they represent. But here I'm trying to present the effect of dispersion on my flow. And this line right here is for d over ul infinity. This have perfect mixing, which is a CSTR, and then d over ul is 0. My curve basically becomes a straight line here through the middle, and this is a PFR. Technically, you don't operate at an ideal PFR, right? You operate somewhere in the middle. So this is d over ul is infinity. This is your mixed flow reactor, and then for d over ul is 0, which is a PFR, this will be, it gets smaller and it gets narrower, probably be something like this. And in a plant, you're not going to operate at a PFR, right? You're not going to operate here. It's not going to happen. However, you don't want to operate your PFR as a CSTR, so you don't want to operate here either, right? Find yourself operating on this line when you have a PFR, then something is horribly wrong. Usually you're going to operate somewhere between these two lines, but somewhere between these two extremes is your performance. And here you can really understand, the effect of your fractional composition of your feed as a function of time, and this will give you an idea of the dispersion, right? So if you can operate at this line, maybe at this line, then you're doing well. PFR, you don't have a lot of dispersion. If I'm operating here, then I have a huge dispersion in my system, and maybe we need to start thinking about different ways to design this reactor for it to behave in a more expected way. Okay, and again, always think about all these different types of charts when dealing with your designing your system. So if you have a first order reaction, there's no change in volume on reaction, and the performance lies between a PFR and a CSTR. And then how, if I have 5 CSTRs in series compared to 1 large CSTR, how this performance be different. If I have PFRs, I want to have it a very long PFR or a bunch of smaller PFRs. All of these simple manipulations can make a big effect on your final design. And again, similarly for this, we talked about these charts before. Okay, let's move on to this idea here. And here, let's have a look at a motivating example. Let's say you have two systems. System one, I have a CSTR followed by a PFR, right? System two, I have a PFR followed by a CSTR. And the determination you need to make is which system is going to give you, which system is going to give you the better performance and why. So CSTR, PFR, PFR, CSTR, which have the same reaction happening, which system is going to give me a better performance? Intuitively at this stage, I expect you to say, well, it depends on the order of the reaction, right? And that's true. It will depend on the order of the reaction. It depends on the nature of the reaction, right? Maybe this configuration is better for a low order reaction. This configuration is better for a high order reaction. And if you have a look at the residence time distributions, you're going to find out that they are exactly the same. Okay, so this is another thing to think about when dealing with these systems. Sometimes, if you want to compare two systems using only one experimental method, you're going to get the same performance. If I use a tracer here and a tracer here, and I have a look, it's going to be the same. It's similar when you took in controls. If I have a pulse signal and I'm adding it to a dying signal, the product will be the same whether I add them A plus B or B plus A. Similarly here, if I add a tracer, I'm going to see that my residence time distribution curve is exactly the same. So I can't make a determination on which system is better just by looking at the tracer system. So now we need to start thinking about the different rules for picking the best reactor. For a single first order reaction, identical conversion will be achieved. For a single second order reaction, system 2 will give me a higher conversion. For a single zero order reaction, system 1 will give me a higher conversion. So the idea here is that for second order reactions, using a PFR followed by a CSTR will give you a better performance than using a CSTR followed by a PFR for higher order reactions. Whereas for lower order reactions, this system CSTR followed by PFR will give you a better performance. For just the first order reaction, they behave exactly the same. And now you need to start looking at the volume of your units and how they're going to affect your economics. Okay, just one thing to keep in mind when trying to quantify the non-ideality. Don't forget other judgments as well, right? So yes, tracer curves are nice. They're easy to look at. They can give you a quick indication. However, sometimes they might not give you the best insight, or they might fail to differentiate between different systems. Okay, so and then finally in this closing slide, out there you can always build complex numerical reactor models. You can have effective changing velocity, axial dispersion, radial dispersion, effective heat, mass transfer, diffusion, catalytic reaction, all of this. And if you want to model this using a system of reactions, you need to identify the appropriate models, build the appropriate mass balances, build the appropriate heat balances, and then you aggregate all your equations, find your degrees of freedom, find which parameters do you have, which parameters do you need to measure, which parameters do you need to estimate, and then you start solving your system of reaction. And throughout your career, if you end up working in a development team, they tend to do a lot of this modeling. If you work in a research team, they then tend to do a lot of this modeling. If you work for a startup where a lot of the ideas are new, you want to supplement experiments with some modeling as well. Okay, so this is the end of this chapter. There's a homework as well. The homework is not too complex, but the solutions, I'm going to post them as well in the week 12 photo. Again, if you have any questions, please come to office hours, and please start thinking about the final, preparing for the final, looking at exam 1 and exam 2. I'm going to post the solutions for them as well, and try to identify which areas you're comfortable with, which areas you want to spend more time on as you prepare for the test. All right, thank you very much.